Hi, I want to talk about black hole spectroscopy with Lisa using quasi-normal mode overtones. And this is work done in collaboration with Iara from UFABC in Brazil. Now, in a compact binary coalescence, the gravitational waveform shows the three stages of evolution of the binary. First in spiral, described by post-Newtonian theory, then the merger, which needs to be described by numerical relativity, and finally the ringdown, which we can well describe with linear perturbation theory. Now, in the very first detection announced by LIGO, GW150914, we can already see all of the three stages of the binary evolution in the waveform, including the ringdown, which is the part of the waveform in which I'm going to be focusing this talk. Now, linear perturbation theory in general relativity shows us that perturbed black holes are basically mass spring systems. After the merger of a binary system, the merging remnant, the final black hole, is in an excited state with extra energy, and it emits this extra energy. Now, this perturbed spacetime is described by the linearized Einstein field equations, which, for the case of a rotating Kerr black hole, results in the Minkowski equation, and the gravitational wave emitted resembles an exponentially damped sine wave like this. The quasi-normal modes are going to be special solutions of the Minkowski equation with appropriate boundary conditions such that what we see are characteristic modes of oscillation. In order to ensure that what we are seeing are free oscillations of the black hole, the relevant physical boundary conditions are waves purely outgoing at infinity and purely ingoing at the horizon. Here we have an example where we can see in the log scale the exponential decay of the quasi-normal modes. So, as they are characteristic oscillations, they are independent from the initial conditions, and therefore they can be considered the fingerprint of the source. One of the most remarkable consequences of general relativity is the so-called no-hair theorem. Now, the statement black hole has no hair is more catchy than the more appropriate statement black holes have three hairs, which are its mass, electric charge, and angular momentum. Now, for astrophysical black holes, out of these three numbers that describe the spacetime, we can neglect the electric charge and only worry about two numbers, the mass and the angular momentum. This, of course, for black holes in vacuum, given that black holes surrounded by matter or other fields can be wearing wigs, which are not, however, intrinsically part of the black hole. We can think about testing the no-hair theorem using black hole quasi-normal modes. Now here I have an example for one specific quasi-normal mode described by the numbers L and M, which give the angular symmetry of the mode. This mode can be described as a sum of terms of this form, where the omegas are complex frequencies, such that the real part is related to the period of oscillation of the mode, and the imaginary part is related to the damping time of the oscillation. Now, in this sum, the terms of n equals 0 are called fundamental modes, and the terms of n larger than 0 are called overtones. These two numbers depend only on the mass and spin of the black hole, and of course also on the underlying theory of gravity, which here we take to be general relativity. Now, from GW150914, it was possible to determine the frequency and damping time of the fundamental mode in the ringdown independently from the spiral and merger part of the waveform, which we can see here in this plot. Now, the fundamental mode is usually how we call the fundamental quadrupolar mode that has numbers 2, 2, and 0. Now, if we can detect more than one mode, then we can start doing black hole spectroscopy. Now that we know that it is possible to detect the fundamental quadrupolar mode, or the fundamental mode, we can start looking for a second mode. We can start by looking for higher harmonics, which are going to be fundamental modes with n equals 0 and numbers Ln different from 2, 2. Now, here in this plot, we see the amplitude of these higher harmonic modes normalized by the amplitude of the fundamental mode as a function of the mass ratio of the binary going from 1 to 1 to 1 to 10. And what we can see is that these higher harmonics become more relevant for unequal mass binaries. Now, almost all of the detections so far have been compatible with the equal mass case, maybe with the exception of the latest detection announced by LIGO, which has a mass ratio of approximately 1 to 4. However, we don't really know what will be the mass ratios for the LISA supermassive black hole binary sources. Are they going to be mostly like equal masses or mostly like unequal masses? We still don't know. Now, in our search for a second mode, we can also look for overtones, which here we are going to consider to be the modes with numbers 2, 2, 1. So the first overtone of the fundamental quadrupolar mode. Now we can see here in this plot that the amplitude ratio between this overtone and the fundamental mode peaks for equal masses and becomes larger than it is for the higher harmonics. Now, there have been preliminary results showing some evidence for the overtone in the data for GW150914. What we can see here in this other plot on the right is that the first overtone is going to have a signal-to-noise ratio, or SNR, lower than the fundamental mode, but is still higher than the next most relevant higher harmonic, which is the mode 330. Now, of course, detectability of a mode is not enough. We need to be able to resolve the two different modes that we want to detect. And for that, we adapt the Rayleigh criterion, which was originally proposed for resolving two bright stars very near each other in the sky. So what we do is that we require resolvability of both the frequency and the damping time for a ring-down mode with numbers L, M, and N by requiring that the difference in the frequencies relative to the fundamental mode be larger than the maximum error in the determination of the frequencies, and equivalently for the damping times. Now, it's also important to note that the frequency of the 2-to-1 mode is very close to the frequency of the 2-to-0 mode, as we can see here, while the frequencies of the higher harmonics are very different from the frequencies of the fundamental mode. But when it comes to the damping time, we note that the higher harmonics, which are all fundamental higher harmonics here, they have a damping time very close to the damping time of the fundamental mode, while the first overtone has a damping time that's very different. So if you want to resolve the first overtone, resolving the damping times is easy, resolving the frequencies is hard. If you want to resolve a higher harmonic, now resolving the frequencies is easy, and resolving the damping times is hard. Now, in order to tap into the enormous potential of LISA and the huge SNR that we expect from the detections, we would like to know what we expect. And what we expect is still rather uncertain. So as we can see here, for the event rates expected per year as a function of the redshifted mass using 3 different models, we see that the projections go from a few events per year to hundreds of events per year. And our uncertainty on the rates reflects our uncertainty on the supermassive black holes that are supposed to be merging. So we have models for the black hole mass function for different redshifts, but we also have a lot of uncertainty on the existing supermassive black hole binaries. Here on this table, I have listed some possible candidates that have been studied, of which the most reliable identification is for OJ287. And we can see that for these candidates, the mass ratio goes from 1 to 1 to 1 to over 100. So they just could be anywhere. We still don't know. Now I want to put the frequencies of the first overtone and the higher harmonic 330 on the LISA noise curve and see what are the trends that we expect, because these are going to be important. For a black hole with a mass 10 to the 5 solar masses, we see here for Z equals 0.001, the frequency of the 2 to 1 mode and the frequency of the 330 mode, which is not quite twice the frequency of the overtone. As we increase the redshifts, the frequencies drift to the left. As we increase the mass of the black holes with a higher mass have lower frequencies. The entire set of frequencies shifts to the left again. As we go to a black hole with 10 to the 9 solar masses, we see that these frequencies are already starting to drift out of the bucket in the LISA sensitivity curve. So we need to pay attention to these details. So here we show finally the black hole spectroscopy horizons with LISA. What we have here on the left-hand side is the redshift, on the right-hand side is the luminosity distance, and here on the x-axis we have the mass ratio. Now the edges of the green bands show the black hole spectroscopy horizon, so the maximum distance up to which I can resolve the first overtone 2 to 1 and the fundamental mode 2 to 0 for these different masses of the black hole. And the dashed orange lines show the corresponding spectroscopy horizons for the higher harmonic mode 330. So what we can see here is that the horizons become larger for lower masses. We can see that they shrink very much for the higher harmonic as we approach the equal mass limit. And we can also see that this spectroscopy horizon is approximately half of the ringdown horizon, up to which I can detect the ringdown modes. So finally, I wanted to say that there are very exciting prospects for testing gravity with LISA. However, the characteristics of the supermassive black hole binaries that we expect to detect are still very uncertain, and so are the rates of these events. We have shown that the resolvability of the first overtone is favored over the higher harmonics for binaries closer to equal masses. And we have showed that the black hole spectroscopy horizon is approximately half of the ringdown horizon. Now, it's very important to keep in mind that for more massive and also for more distant supermassive black hole binaries, most of the SNR will be accumulated from the merger and ringdown. Therefore, higher harmonics and also overtones must not be neglected in the modeling of the waveform. Thank you very much. This is all that I had to say for today.